This is section 9.5, part 2. All right. Now I'd like to turn to a new idea, the signs and ranges of function values, the trigonometric function values. Let's start off with the idea that I said pretty early on last time, that r is always positive, which means it's never 0. If I look at some first quadrant angle, so we're going to land in the first quadrant somewhere, then the point in the first quadrant that the ray will go through, let's just say it's this ray, will be some xy, and that means that in that quadrant at least, x will be positive and y will be positive. So if all three of those are positive, every single ratio, x over r, x over y, y over x, y over r, r over x, r over y, positive divided by positive will always be positive. So in the first quadrant, all trig function values are positive. Okay. Now, in the second quadrant, I'm not going to draw as much. In this quadrant, x is always negative and y is always positive. And so in thinking about the ratios, if x is involved with either one of the other two, you'll have a negative answer, because if x is negative and you divide it by or into a positive answer, the answer will be negative. So anything that involves x will be negative. So what is positive? That's kind of the big question. Well, y over r, positive divided by positive, and r divided by y, positive divided by positive. Those will be positive. Well, what are those? Well, that's sine and its reciprocal cosecant will be positive in quadrant 2. Okay, so let's go to quadrant 3. Well, in this quadrant, x is negative and y is negative. So if you have x with r or y with r, you'll have negative and positive, so that answer is negative. In fact, the only positive answer you can get is if you divide negative by negative. So y over x and x over y will be the only positive answers. So that's tangent of theta and cotangent of theta are the only positive function values in quadrant 3. Okay, and then finally, quadrant 4, x is positive and y is negative. So, what's going to be positive? Pause the recording and see if you can figure it out on your own. Okay, so since y is negative, y operating with either x or r, both of which are positive, will give you a negative answer. The only positive answers come with x and r being used. So x over r and r over x. That is cosine of theta and secant of theta, its reciprocal, are the only positive valued functions in quadrant 4. Meaning everything else is a negative answer. So notice that those go with their reciprocals. Cosine and secant have the same rule. They're positive in quadrant 4. Tangent and its reciprocal cotangent are positive in quadrant 3. Sine and its reciprocal function cosecant are positive in quadrant 2. So to remember this, and I don't know if this is really super duper important, because I think if it were me, I would just figure each one out individually as things came up. But someone came up with this cute little thing to remember this, and I guess I'll give it a nod. So this is going to be which functions are positive in each quadrant is kind of the name of this little bitty thing I'm going to create for you. Like I said, it's kind of silly, but if it helps you and you get things right because of it, I suppose it's worth it. So in the first quadrant, they're all positive. All 6 of them are positive. In the second quadrant, it's sine and it's reciprocal. So I'm going to write S because that's the major function, and you'll just have to remember that its reciprocal does what it does. So tangent in this one and cotangent, and in this one cosine and secant. So the way to remember this is if you go through from first to second to third to fourth quadrant is this little public relations it's a public relations announcement for the day. All students take calculus. Isn't that silly? Well, no, it's not. I hope you take calculus, that you're in pre-calculus, so it seems logical that you might at least be considering taking calculus. So all students take calculus is a silly little mnemonic to help you keep straight which functions are positive in each of the 4 quadrants. If that helps you, great. If it doesn't, well, no big deal. My feelings are not hurt if you don't get it. All right. So, and there's a table on one of the slides where they have it, where each of the quadrants is listed and a plus or a minus sign for each of the functions. And I suppose that's just another memory thing. And you can memorize that, or you can memorize all students take calculus, or you can do what I would do and just figure it out as I go. You'll know the definitions. Sine of theta is y over r. If y is negative and r is always positive, you know the answer is negative. If y is positive, r is always positive, you know the answer will be positive. And you don't have to worry about memorizing something. Just take it as it comes and deal with the x's and y's that you're dealt with. Of course, r is always positive. All right, so what kind of question might we encounter here? A, identify the quadrant or quadrants of any angle theta that satisfies sine of theta is positive and tangent of theta is negative. Now you could go and look at the table or look at all students who take calculus. Yeah, okay. That's not something I'm going to remember as easily as this. The definition of sine of theta is y over r. If r is known always to be positive, the only way that fraction is positive is if y is positive, right? And then tangent of theta is y over x. And if that answer is negative, and we've already determined that y has to be positive, the only way that fraction can be negative is if x is negative. And so in which quadrant is y positive and x negative? What quadrant is that? No, it's quadrant 2, right? It's not that bad. Figure out. Okay, let's do another one. B. Identify the quadrant or quadrants of any angle theta that satisfies cosine of theta is negative and secant of theta is negative. Okay, cosine of theta is x over r. Since r is always positive, that means x is the thing that has to make this negative. Secant of theta is r over x, and it's supposed to be negative. And since r is always positive, the only thing that's going to make that fraction negative is if x is negative. And we got the same information twice. Because they're reciprocals, that makes sense. whatever sign the cosine has, if it's positive, its reciprocal is positive. If the cosine has a negative answer, its reciprocal is negative. So that's no new information. So there's no information that we're getting about y, which means y can be anything, positive, negative, 0, whatever, right? So in what quadrant or quadrants does that happen that x is negative? All right, it's quadrant 2, where y is positive, and quadrant 3, where y is negative, all the while x being negative. So that's that. So theta could be in either of those two quadrants. Okay, so let's think about how we're getting these answers. There's some pictures drawn, and I hope they included them, but I'm going to do my best to sort of recreate them, at least to a certain extent. So, so we have an angle in standard position. So the initial side, of course, is here, and the terminal side is wherever. And I'm going to focus on the first quadrant, and then we'll extrapolate this to include the second quadrant. If theta is really close to 0, it's a really small angle. If we were to draw our triangle, this would be x, this would be y, and this would be r. And let's think about sine of theta. That's what I'm wanting to focus on right now, is sine of theta. And you could do this for all of the 6 trig functions with this same idea. In fact, what I'm going to do is I'm going to do it really well with sine of theta, and then just give you the answers for the other 5, assuming that you could go through this same thinking process with them. Okay? So that's how we're going to attack this. All right. So y over r here, y is pretty small compared to r. So this is really close to 0. Think of like if y were 0.1. It's drawn kind of big so you can see it, but think of y as being like 0.1, and r could be like 1,000. 0.1 divided by 1,000 is really close to 0. So as long as your theta, which I didn't draw the theta in here, it's that angle, I'll call it theta out here, the sine of that angle, y over r, will be really close to 0. Okay? Now, as we rotate that angle through the first quadrant, so we started with y being kind of small, so here's this, and then we have maybe something like this, kind of a middle kind of value. I'm not trying to make it exactly 45 degrees, just some middle value. This would be y, this would be x, and this would be r. And now y over r, those are kind of close, but notice, because it's a right triangle, the hypotenuse r is always bigger than the leg y. So this is going to be some number that's, less than 1 for sure, right? Right? Because small over slightly larger, like 3 over 4 or 7 over 9 or something like that, that's less than 1, right? Okay, then at an extreme, and that's what we were trying to do with the first one and the last one, is we're kind of looking at extreme situations within the quadrant. So here's your initial side. Let's say this is getting really close to 90 degrees. Okay, I'm going to have to draw it so it's not that close, so I can actually draw the picture. But we're thinking here that that's almost 90 degrees. So kind of keep that in mind as I'm drawing this. That's what we're trying to make it do. So here's x, here's y, and here's r. Well, the further up we go, this fraction y over r is getting closer and closer to what? Well, if you remember the quadrantal answers, sine of 0 was 0, right? Sine of 0 degrees was 0. So that totally makes sense that when the angle is really close to 0, y over r is going to be close to 0. And y over r, that y is getting to be almost the same length as r. So this is getting closer and closer to 1. And in fact, that makes sense. If you look back at the quadrantals that we did earlier, the sine of 90 degrees is 1. And so, since our fraction is y over r, the extreme value is, for a high value, is 1. Okay? And we can have other fractions between 0 and 1, and that would make sense, right? Okay. Now, what if we're in a quadrant where y can be negative? By the way, this same argument would be this exact same idea in Quadrant 2. Really close to 180 degrees. This would be 0. And y over r would be a positive number that's less than 1. And, of course, sine 90 degrees, the beginning of Quadrant 2 is at the y-axis, that's 1. So all of our answers so far are between 0 and 1 inclusive. So far, okay? So far, that's what we have. So let me write that down. What we know right now is that sine of theta is less than or equal to 1. And we would say for right now, let me put this in a different color. For right now, in the first and second quadrants, we're bounded on the bottom side by 0. That's not going to stay true for much longer, so don't get too excited about that. Okay, so let's say we're in the third or fourth quadrant, and it won't matter which one I draw this in. So if you don't mind, I'm going to use the fourth quadrant, since it doesn't matter. Oops, hold on. Let's say that we're, oh, dang it. Yeah, that's fine. Let's say we're almost all the way around to 360 degrees. Okay, so the angle I'm thinking of goes all the way around like that. Okay, so if I draw a point on the terminal side and draw that triangle in, y is tiny and negative, and r, of course, is positive. And so we're going to have y over r, where y is tiny compared to r, that's really close to 0, but negative. Y over r here is a negative value. Then, if we go, I'm going to skip the middle one because it's just not going to make that much of a difference. It's still going to be y over r, and it'll be a negative number for a middle value. So I'm going to kind of skip drawing that one for the sake of time. And the other extreme would be if it's really close to 270 degrees. Okay. So it's really close to that negative y-axis. So if I have a point on here, and draw this in, there's my x, y is negative, and that's r, and y and r are almost the same length. So again, y over r is really close to the same length. So you'd like to say 1, but remember y here is negative, so it's getting really close to negative 1. And so as it turns out, this being bounded below by 0 is actually not true. It's actually bounded below by negative 1. So let me write that over here a little bit cleaner. All answers for sine of theta are between negative 1 and 1 inclusive. Those are all the values you can get for sine. Like if someone came along and said, hey, I found sine of 12 degrees is 16. You need to laugh in their face because that's impossible. If someone takes the sine of any angle no matter what angle they're taking it of, the answer has to be -1, +1, or something in between those two. That's it. Okay? So, that gives us an idea of the range of sine of theta. So if you turn to another slide, a couple of slides later, I think it is, oh, well, that's okay. Well, let me say this, because I think this would be important. If we take the reciprocal r over y, which of course is cosecant of theta, r is bigger than y, right, for all these triangles we drew. So if I do the reciprocal and I have like, I don't know, 1,000 is r, and I'm exaggerating, and y is really tiny, like 0.1, well, cosecant of that, it's going to be 10,000. So those answers just get bigger and bigger. And so as it turns out, and if y is negative, let me make up another one. If y happens to be negative instead of positive, then r over y, r is still relatively big. Let's say this is like is like 2 over, I don't know, -1.99. What's that close to? Well, obviously I try to design it so that's really close to -1. And that's about the smallest, because remember 2 is always longer than y. I mean, r is always longer than y. So at an extreme where they're almost the same, I'm going to get -1. So what that means is that any cosecant answer you get is less than or equal to -1 or greater than or equal to +1. So if you take a proper fraction, which is what we're talking about for sine, if it's between -1 and 1, it's what we call a proper fraction. The numerator is smaller than the denominator. The reciprocal of any proper fraction is beyond 1. And let me just talk about positives because that makes it easier. The reciprocal of like 2/3 is 3/2, bigger than 1. The reciprocal of 9/12 is 12/9, bigger than 1. The reciprocal of 99/100 is 100 over 99, bigger than 1. So every reciprocal of a proper fraction is greater than or equal to 1. And then, of course, if you have a negative involved, it'll be less than or equal to -1. So these are the ranges in a table that I'd like for you to look at. They do go kind of pairwise. Let's see. So for sine and cosine, they actually have the same range. They are cofunctions, so they have a lot to do with each other. The range is all answers will be between -1 and 1 inclusive. And that's, of course, using interval notation. And I hope you're familiar with that. If you're not, then ask me about it in class, and I can go into it in more detail. And what that means is that the bracket, the square bracket, means includes the number, and the low number, -1, is on the left, comma, larger number on the right. And that implies that every single real number in the interval from -1 to 1 is valid. So it's a continuous set of numbers from -1 to 1, and the brackets mean include that number. If you don't want to include something, like if you were graphing something like 3 to 7 and don't include 3 but do include 7, that would be the interval of all real numbers from 3 to 7. To show that we're not including 3, we make a parenthesis. To show that we're including 7, it's a bracket. Okay, so that's what that is in interval notation. cosecant and secant cofunctions, of course, have the same range as each other. And what that is this, an interval notation from negative infinity to negative 1 inclusive, union from 1 to infinity, which is basically what this means in interval notation. That's the same thing as what's up there. And then for tangent and cotangent, again, those are cofunctions, so they have the same kind of range. That's any real number from negative infinity to infinity. Okay, so those ranges. Now, they show you set builder notation, which I don't think you have to learn, but I'm going to show you what it means. I'm going to rewrite this in set builder notation now. For each of the 3 possible ranges. And these are ranges of the trig functions, by the way. Okay, so in set builder notation, you tell me what variable you're using. And so the answer to y equals sine of theta, or y equals cosine of theta, etc., all these are y equals that. That means that the values that y can take on, the outputs, the dependent variable is y. We're going to use y, so we describe that. And then this bar is read as such that. So this is the set of all values of y such that. And then what comes behind that is a description of those y values. And another way to say that there are numbers between negative and 1 and positive 1 inclusive is to say that their absolute value of that y value, anything between negative 1 and 1, if you take its absolute value, the answer will be less than or equal to 1. And that's the same thing as that. Okay? The second one is the set of all values of y such that the absolute value of y the absolute value of any number that's less than or equal to negative 1 or greater than or equal to 1, the absolute value of it is greater than or equal to 1. Okay? And that's the same as that. And then this one is y is the range is the set of all values of y such that y is a real number. You can use words, you can use inequalities, you can use all kinds of different symbols in this set builder notation. And that would be, I really want you to know interval notation. So I'm presenting set builder because they do, but I'd really rather you focus on the interval notation. Okay, so given those ranges, we're going to talk about what's possible and what's impossible. All right, so for example, A. Someone says sine of theta is square root of 3. Now you need to realize, even without a calculator, you should realize that the square root of 3 is bigger than the square root of 1 and smaller than the square root of 4. So square root of 3 is between 1 and 4. It's not 1. It's bigger than 1. It's between 1 and 4. So is it possible for sine of theta to have an answer that's bigger than 1? Well, if you look at the range, the largest value you could have for sine of theta is positive 1. So this is clearly impossible. Okay. B. Someone says that the tangent of theta has an answer of 110.47. Possible or impossible? Well, if you think about the range of tangent, it can be any real number, and 110.47 is a real number, so that's definitely possible. Okay. So that's not that hard. As long as you know the ranges and domains, you should be fine with these types of questions. How about the secant of theta is 0.6? Well, clearly that's a number that's between -1 and 1. It's not bigger than 1, nor is it smaller than -1, so this is very much impossible. Secant and cosecant can't have any answer that's between -1 and 1. Like 0.6 or -0.9 or whatever, those are all going to be impossible for those. Okay. All right, so now I'd like to turn to a different topic. Specifically, I want to develop a few more identities. So I want to start for these identities with the Pythagorean statement we made at the outset that x squared plus y squared will be r squared. And that's going to be true whenever we have one of these situations that we've been describing. We have an initial side and a terminal side someplace, and forgot to label the axes. I just talked about that. Shame on me. So we have an initial side for the angle, we have a terminal side for the angle, and then we pick any point we want on that terminal side and draw a line segment down to the x-axis, and that should be perpendicular to the x-axis, and that will create a situation where we have x, y, and r, as we've been doing. And of course, because of that right triangle, the leg squared plus leg squared equals r squared, hypotenuse squared. So this is something that's always going to be true. All right, so because x squared plus y squared equals r squared is an always true statement, something you can do to equations is, if you want to, divide both sides of the equation by the same thing. As long as you're not dividing by 0, it's all good. And r is never 0. So I'm going to divide both sides by r squared. On the left side, that's going to end up, when I split that fraction into x squared over r squared plus y squared over r squared equals 1. And then if I wanted to, I could write that as x over r quantity squared plus y over r quantity squared. And as a reminder, what I'm using there is the rule about powers, that if you have a quotient raised to a power, you distribute that exponent to the numerator and denominator separately. And that's what I just used, but in reverse. I had x squared over r squared, and I rewrote that as x over r quantity squared, for example. Okay. Oh, and the other thing I did algebraically, I guess I can mention that. You know that if you're adding or subtracting fractions that have the same denominator, that means that you add or subtract the numerators and put that over the common denominator. And that's what I did in a prior step, splitting that fraction into two fractions, when I made x plus y squared all over r squared equal to x squared over r squared plus y squared over r squared. That's what I was doing. So there's all kinds of little algebraic things that you're supposed to still know how to do that I'll try to remind you of as I use them, like I just did that. Okay, now x over r, what is that the definition of? X over r. Well, that's cosine of theta, right? Squared. Plus, what's y over r the definition of? It's the definition of sine of theta. And because the first equation is always true, and dividing both sides by r squared doesn't create any falsehoods, we haven't divided by 0, and all we've done is logical, legal, mathematical steps, including the two steps that I demonstrated over to the right side, and then the substitution according to the definition of cosine theta and sine of theta, this is a true statement. Okay? And it's always true. No matter what angle theta is, the cosine theta answer squared plus the sine of that same theta, that answer squared, if you add those up together, it will always equal 1. Now there's a convention that we use for powers of trig functions that we really don't like to see extra parentheses when we can avoid them. So what we're going to write that means exactly the same thing as squaring the answer to sine of theta is to write sine squared theta. And that's what it means, is the sine of theta then squared. So this is a little bit nicer notation, and you just have to remember that what it means, like if you're doing this on your calculator, you take the cosine of theta, get an answer, and then square it for cosine squared. So just to let you know, this is an abbreviated version, and that will always be what we use for powers of trig functions. Okay, so that is what we call a Pythagorean identity. So I'm going to list those over here, and these are ones that you will need to memorize. So add these to the list of your memorized formulas. And we're going to have several Pythagorean identities, so I'm going to list them over here all together. And sometimes I change the order just because I like to. So I just want you to know that writing sine squared theta plus cosine squared theta is the same thing as the reversal around that addition sign. And so I might very well write the first Pythagorean identity that way, or the way it is over on the left side. They are the same thing. Okay, now let's say that we start with the Pythagorean relationship. Again, x squared plus y squared equals r squared. And this time I want to divide everywhere, or divide it both sides by x squared. Okay, so if I do that, that's going to end up being x squared over x squared plus y squared over x squared equals r over x quantity squared. And so x squared divided by itself is 1. I'll rewrite y squared over x squared as y over x quantity squared. And I've already done that on the right side. Okay, so now let's use the trig definitions of y over x is what? That's tangent of theta. So tangent of theta quantity squared is what I would write, but I'm going to go ahead and go straight to the abbreviated version. Oops, forgot to write the n. Silly me. And write tangent of theta squared is tangent squared theta. R over x, what is that? Well, that's secant of theta, that it will be squared, and the abbreviated form of that is secant squared theta. So that's the second Pythagorean identity. And again, these are all things that you should commit to memory. Okay, the last one of those. X squared plus y squared equals r squared. We've divided both sides by r squared. We divided both sides by x squared. What's left? Well, I'd like you to pause the recording and see if you can follow through and develop what the third Pythagorean identity is. Third of 3. Okay, do that by yourself. Hopefully you thought to divide by the only thing we haven't divided by yet, that is, namely y squared. So that'll be x squared over y squared plus y squared over y squared equals r over y quantity squared. And so this will be x over y quantity squared plus 1 equals r over y quantity squared. x over y is cotangent of theta. The square of cotangent theta will be written as cotangent squared theta plus 1. And r over y is cosecant theta. The square of that will be cosecant squared theta. And there's your third and final Pythagorean identity. Cotangent squared theta plus 1 equals cosecant squared theta. All right. All right. So now let's move on to some more identities. What I want to do here is I want to form quotients, ratios of two trig functions and see what happens. So for example, sine of theta over cosine of theta. I want to investigate what that might be. Well, by definition, sine of theta is y over r, and cosine of theta is x over r. That's a legal substitution. We can do that. And to divide fractions, you take the numerator fraction and multiply it by the reciprocal of the denominator fraction. In this case, the r's cancel out, leaving y over x. And that's equal to what? What is y over x always equal to? Well, it's the definition of tangent of theta. So I'd like for you to explore cosine of theta over sine of theta and see if you can figure out what that's equal to. Okay. Hopefully you got x over r divided by y over r by substitution, which is x over r times r over y by definition of division. And simplification leads me to x over y, and that's the definition of cotangent theta. So this pair of identities are called quotient identities. I will sometimes call them ratio identities because that's the name I learned when I first learned these. So if I accidentally say ratio identities, you'll understand that I mean these quotient identities. That is that tangent of theta is equal to the quotient of sine theta to cosine theta, sine theta over cosine theta, and that cotangent theta is the quotient cosine theta over sine of theta. Okay, and again, these are to be memorized, so make sure that you are taking all of these things that I say, and this is to be memorized, and make sure that you're doing those memorizations. Okay, I'm about to run out of room down here. No, I think I have a little bit more. Never mind. Next problem, example. If tangent of theta is known to be 4/3 and theta is in Quadrant 3, our task is to find sine theta and cosine theta. Okay, so what can we do for this? Well, I'm going to try to use some of the identities we just learned. It would be a fallacy to say, let's let tangent theta be sine theta over cosine theta and set that equal to 4/3 and then jump to a conclusion that that means sine of theta is 4 and cosine of theta is 3. Because remember, that's not in the range. Sine of theta and cosine of theta only give answers between -1 and 1 inclusive. So sine of theta being 4, for example, is impossible. So that's not the identity that will really help us here. What I'm thinking of is one of the Pythagorean identities. 1 plus tangent squared theta is equal to secant squared theta. So let me see. By substitution, I can put 4/3 in for the tangent of theta. The square of 4/3 is 16/9, plus 9 is 25/9. And taking the square root of both sides, secant of theta is plus or minus. The square root of 25/9 is 5/3. And then we have to pay attention to the information that theta is in quadrant 3. And in quadrant 3, all students take, tangent and cotangent are the only positive trig functions in that quadrant. So secant and anything else in that quadrant would be negative. So I'm going to circle this negative sign to indicate that that's the one I'm interested in. Okay, so now we've established that secant of theta is negative 5/3. Well, now I'm going to use an earlier identity, the reciprocal identity. The reciprocal of secant is cosine theta. So I can substitute for secant theta with 1 over cosine theta, and then take the reciprocal of both sides of the equation, which, by the way, that's a valid technique. Take the reciprocal of both sides of an equation is valid. And there we have cosine of theta. Well, now that we know that's true, how are we going to find sine of theta? Well, we do have the trig identity sine squared theta plus cosine squared theta equals 1. And now that we know that cosine of theta is negative 3/5, I can solve this equation for sine squared theta. That'll be 1 minus 9/25, which is 16/25. And so sine of theta is plus or minus the square root of 16/25, which is 4/5. And then quadrant 3, tangent and cotangent are the only positive things there, so sine of theta will have a negative answer. And so our conclusion would be that sine of theta is negative 4/5. And so we have our two answers. Here's the cosine of theta answer. Here's the sine of theta answer. Okay, so I think now I'm gonna, I've run out of room, so I'm gonna close this recording and open another one.